Hello all. So, today this is our second lecture for VLSI design, the course code KEC 072. So, today we are going to have a detailed information on critical path, worst case timing analysis and overview of design hierarchy. That part we are going to finish in this lecture. So, first we have to understand what is critical path. Okay. So, critical path means the circuit that can take the longest time, that is called a critical path. So, we have to find out what is our critical path in the particular circuit, that we will see. So, we can define it as a critical path is the longest path in the circuit that limit the clock speed. Okay, means beyond the critical path, if your circuit are taking much larger time or much higher time as compared to the critical point, if you are setting the critical path, then the device does not function as desired. Okay. So, the path between the input and the output with the maximum delay, that can be a critical path. So, if we see this circuit, so here you can observe that here we are having a 3 gate, one is AND gate, OR gate and again AND gate. So, we are having 2 AND gate, 1 OR gate. So, you have to find out the critical path which are taking a maximum delay. So, here you can see here we are having a 1 and here it is second. So, 2 gates. So, if you are finding a critical path, that is the longest path, then the delay, the propagation delay in terms of time. So, you can see that we are having twice the delay of the AND gate. Why we are taking the twice the delay of AND gate? Because we are having 2 AND gate. So, we are multiplying with the 2. So, whatever the delay is exhibiting by this AND gate and this gate, that should be multiplied by 2. Now, plus we have to also take the delay of this OR gate. So, from here you can observe this is the maximum delay offered by this entire circuit. So, to when we are having an input A and B at this gate and the output Y will have this much of delay. Similarly, if you talk about a shorter delay, then you can see that the input D, this input D is directly connected with the last gate and you will get the output instantly. So, the delay if follow this path will have a shorter delay. So, you can see it, this is the shorter delay, clear. Now, the timing analysis. So, what kind of things we have to take care? So, timing analysis basically means measuring the speed of the circuit, that means you have to measure how fast your circuit can behave, and then the estimation of critical delay, that we have just talked about the critical delay. Then the slack determination means what is the difference, what is the actual output and how much the expected output. So, difference will be a slack determination. So, slack determination should be there. Okay. You have to obtain the particular difference. So, how much you are lacking with the performance. Then the critical path identification, you have to also find out that this path is taking much larger time. So, what is the goal of this timing analysis, that also we have to understand. So, the first is the circuit meets the timing specification, because at the time of designing the circuit we should have some kind of specification. Yes, this circuit should take this much of time to produce the output there. And second thing, there are no functional violation due to timing error, it should not have any violation, means no rest around conditions. So, now we have to see worst case timing analysis. Okay. Now, to understand the worst case timing analysis, we have this, we can understand by mean of this picture. So, SRC, this is a source terminal and this is a shrink terminal. Okay. So, now from here to here, suppose there is a one intermediate node, that is N. Okay. So, we have to first find out what is my AT arrival time and what is required arrival time. Okay. That we will see by mean of a formula. So, in order to identify the worst delay, we need to define the two important points. One is arrival time at the node. Okay. Suppose this is my node, this is my node, at what particular time it reach from source to that particular node, and then the required arrival time. Okay. So, what should be the required arrival time to reach to this particular destination? So, the arrival time at the node is the longest path from the source to the node. After that, we need to compute this arrival time at each and every node. Suppose in your entire circuit you are having several number of nodes, then you have to take care and you have to compute all these particular time, arrival time. So, this can be understood by mean of this formula. Suppose this is my u and this is my node v. Okay. Then the arrival time at this particular node v, so AT of v is equal to maximum, you have to find out the maximum delay or maximum time you have to find out. So, what is my maximum out of all other node? Okay. So, that is should be AAT of u, the previous node, and the time required from u to v, that we have to check. Clear? Now, similarly, we are also having a required arrival time at the particular node. So, the latest time the signal is allowed to leave the node to make it to the sink in the time. Okay. So, that we can see while calculating the rate, that is required arrival time, you have to take a minimum time. How much minimum time? So, we have to go backtrace, we have to backtrace this entire node, and then we have to find out the minimum time. And how you can find out this minimum time? You have to find out the difference of this, you have to be in the particular u node means the previous node, and then you have to subtract the time that is between the node u and v, that we will see in the numerical, this portion. Then the slack. Now, the third point, you have to understand how we can calculate the slack. Now, you have at the first stage you have already calculated the arrival time, in the second stage you have calculated the required arrival time. Once you take the difference of this rate and AT, you will get the slack. Okay. That will show you the difference, how much time you are lacking with getting the actual output. Clear? Now, we can understand this thing by mean of this example. Okay. So, in this example you can see we are having 3 input A, B and C, these 3 are input. Now, apart from these 3 input, we are having these wires. Okay. This is my wire, this is my wire, okay, and these are the gates, we are having a different gates. Clear? Now, you can see we are having some kind of weightage for this particular path and we are having some kind of delay weightage for this gate. So, you can see 8 for this gate to reach, we can treat it as a y. Okay, this is y, this is x, this is z and this is w. So, A to gate y, we are having a path delay of 0.15. Okay, this is my weightage 0.15. Now, the delay of this you can say gate is having 2. Similarly, from B to NOT gate x, we are having 0.1 and the delay of this NOT gate is 1, right. Similarly, C to OR gate Z is having 0.1, between this we are having 0.3, 0.2. So, we are having some kind of weightage. Instead of having unit weightage or unit delay, we are having some different weightage. Now, we have to find out the worst path and we have to check if it meets a cycle time of 5.5. Clear? That we have to check whether whether the designed circuit is meeting that particular time or not. If it is not meeting that particular time, then we have to find out what is the slack, what is the difference, okay, how much we are lacking. So, first to simplify this, we have to convert into direct acyclic graph. Okay. So, here you can see that this A, B and C. So, before that we are having some source here which are generating this thing, and here we are having a destination. Clear? So, at the source we have arranged this source, okay, and the weightage of this 0 second, you can assume. Clear? Now, the weightage of this input point is also 0, A of 0, B of 0 and C of 0. Clear? So, we have converted this thing up to this portion is okay. Now, from A to gate Y, from A to gate Y of 2, we are having a weightage of 0.15, that we have simplified here. Now, again from B to not get x, B2 not get x, we are having 0.1, okay, and from input C to OR gate we are having 0.1, this one. Now, at Z of 2. Similarly, from Y to W we are having 0.2, and this Z to W we are having 0.25, and this from W to F, output F, W to output F we are having 0.2, and this F is having 0 weightage, clear. Now, we have to simplify this circuit, you can say this graph, and then we have to find out three things. One is arrival time, second is required arrival time, and the third is slack. So, I have kept the same diagram here also. Okay. Now, we will see one by one how we are going to find out the arrival time. So, we have to compute the arrival time, that we have to first find out here by using a maximum value of between the node u and the time. So, we are adding these times. Okay. So, we are adding this time here. Now, you can observe that first we have to take care of three things: previous node maximum total value, new node gate delay, and the wire delay, clear. So, this is the wire delay and this is the gate delay, clear, and if we are finding here, then this will be the previous one, clear. So, first here AAT will be 0, okay. Here also it will be 0, clear, because this is a 0 previous one. This will be also AAT is equal to 0, because if you are calculating at this node, then at the previous we are having 0 and the path delay is also 0. So, the total value will be 0. Here also if you are calculating AATs, then you can see that the previous here you are having a 0 and path delay is also having a 0. So, if you add these two, you will get 0 only. So, here also you will have 0, clear. Now, in the last one, in the gate C, in the input C, you can observe that the previous AAT is 0, previous one is 0, but the path we are having some kind of delay, clear. So, this delay is 0.6. So, if you add up these two things, you will get 0.6. So, AAT, the computed AAT will be 0.6. Now, you have to leave the previous value, now you have to update it, each node should be updated. So, now this value is updated to 0, this will is updated to 0, and this one is updated to 0.6, clear. Now, suppose if you want to calculate at point x. So, this is my point x where I have to calculate. So, this is my V and this will be my u point, clear. So, if you want to calculate, so you can see that the previous node. So, this one is my previous AATU, AATU is my 0. So, here you can put it as a 0, this one, and now previous one is 0, and now you have to add, because this one is the sum of all the delay of the node. So, here the previous node will be 0 and here the current node is having plus 1. So, sum of all the delay of the gate. So, 0 plus 1 will be 1, and plus you have to add the delay of the path. So, this delay of the path is 0.1. So, you can see that 0.1. So, if you sum all this, it will become 1.1. So, here AATs will become 1.1. Now, instead of x 1, now we can treat it as a 1.1, clear. Now, if you are going to calculate at point y, then again you can see the previous one we are having previously. Now, previously you have to assume it as a 1.1, see 1.1, and then the current node you are having 2, and plus you have to find out the delay of the path, that is 0.1. So, the total if you sum it, it will become 3.3. So, here you will get 3.2, clear. Similarly, if you are going to find out at this Z, you will have to follow the same thing. Then again previous one is 1.1 and the current one is 2. So, 1.1, 2 and the path of the delay 0.3. So, it will be 3.4. Now, next is your W at point W, clear. At point W you have to find out the maximum. Now, here is a trick. Now, in this particular node the two path is coming, clear. So, you have to find out the maximum one, you have to find out the maximum, which one is giving the maximum delay. Okay. So, if you take this point 2 plus 2 is 4. So, 2 plus 2 if you take this one and plus 0.2. So, it is 4.2, but if you take this path it will take at point W it will take 3.4, the new one is this one, and 2 and plus path 0.25. So, total will become 5.65, which is greater than this 4.2. So, we have to consider this one, clear. So, 5.65, and at the last you will have 5.65 plus 0 and then plus the path delay 0.2, it will become 5.85. This will become 5.85, but our requirement will be how much? This is 5.5. Our requirement is 5.5, right. .5 is our requirement. So, that we are not meeting. So, we have to compute RAT, okay, required arrival time, that we have to calculate for at each node. Now, while calculating the RAT we have to go from the back side, we have to go from here. So, we know that here we expect, clear. So, our expectation that we have given in the question, that is RAT is required is 5.5, the required time is 5.5, but arrival time that we are getting 5.85. Okay. So, we have to check it. So, to calculate this thing we have to look at the minimum value and then sum of all the delay of the gate, and we have to subtract it with the path delay, clear. So, here if you are going to calculate it, you can see one by one. So, 5.5, okay, this is my actual, clear. 5.5 minus 0 if you are calculating at W, clear, if you are calculating at W. So, required time is 5.5 and the value is, so this one is my U and this one is my V, clear. So, 5.5 is my required value, that is my required, but the value of this is 0. So, minus it will go with the 0.2. So, the total will be become 5.3, clear. If we are going with the second one, now this one is updated. Now, for the 5 at point W you can see my value is 5.3, okay. My required value is 5.3, but the actual point that we are getting is 2, clear. The actual point that we are getting 2 here. So, 5.3 minus 2 and minus of this 0.25. So, this will become 3.45, clear. Similarly, if we are moving ahead to this y point, then again you can see that 5.3 minus 2 and minus 0.2, this one. So, you will get 3.1. So, we are having 3.1. Now, at point x, so at point x we are again having a 2 points. So, it can be 3.05 minus 2 and minus 0.3, that will become 0.75, clear. Similarly, at point C you are having 3.05 minus 2, that is minus 0.1, that is RAT 0.95. So, similarly, you have to calculate at point B and at point A, likewise you can go with it. So, at this source you will see you are having minus 0.35, that is the difference. Okay. So, minus 0.35 you are having, you are lacking with the expectation. Clear? So, these are the things you have to see. Now, after that we have to compute. Now, we have calculated the arrival time, we have calculated the required arrival time. Okay. So, now this is I have summarized all in single. Clear? So, this A is your actual arrival time, this R is your required arrival time. Okay. That thing we have mentioned here. Now, we have to find out slack. So, how to find out slack? Slack you can find out by taking the difference between the required and the actual. Clear? So, if you take the difference, so here if you take the difference of these required minus arrival. So, minus of 0.35 minus 0 will become minus 0.35. So, you will get the slack as a minus 0.35. Similarly, at this point again 0.95 minus 0 will be 0.95, here minus 0.35 minus 0 is minus 0.35, here 0.95 minus 0.6 you will get plus 0.35. Okay. This is the difference. Similarly, here if you take 0.75 minus 1.1 you will get minus 0.35. Here if you take the difference of 3.1 minus 3.2 you will get minus 0.1 as a slack. Here if you take 3.05 minus 3.4 you will get minus 0.35. Similarly, if you take at gate W you will again have 5.3 minus 5.65 you will get minus 0.35. At the last the difference you will get minus 0.35. This is how you can compute the slack, right. Now, we have to trace the longest path. Now, we have to trace the difference path. So, you have to look at which particular point you are getting minus 0.35. So, you have to trace all minus 0.35. So, you can see this one is minus 0.35, this one is minus slack 0.35, then again this one is minus 0.35, then you can move to this one minus 0.35, then here you can move minus 0.35 and then finally, you can reach to destination. Clear? Now, once you are here you have to trace it. Okay. So, these are the points that you have to look. So, if I will draw a graph, if I will trace all this minus 0.35 point. So, here you can see we can run it from here to here, then you can trace it here, then here and then here. Clear? So, this is how you can compute the worst case time. So, this is my worst path. Okay. So, you can easily say that this is my slack. So, you have to trace wherever your slack point is minus 0.35. So, everywhere if you select it you will get it. Clear? So, this is how you can calculate it. Now, we can also go for the design hierarchy. So, how, what kind of technique or methodology we are adopting to design particular big blocks. So, we are not going to design the entire block in once. So, what we are doing, we are dividing it in a different modules and then we are separating all the modules, we are implementing individual modules and then at the last we are combining all the modules to get the desired output. So, basically it is called a divide and conquer techniques. Clear? Like suppose if we are having a 16-bit adder, then what we can do, we can divide this 16-bit adder into 4-bit adders. So, we have a smaller module. So, how much time it will take to create a 4-bit module, okay, that we have to look. Then it can also reduce the complexity of the circuit. It can also easy to implement if you reduce the module. So, this reduction can be done until unless you are having a last step points. Okay. So, further this 4-bit adder can be divided into 1-bit adder, that also you can do. So, this 4-bit adder again divided into either half adder, 4 half adder. Okay. So, either you can divide it in 1-bit adder. Now, apart from that, so this 4-bit adder we have already divided, then half adder we have again reduced it to half adder. Then again the half adder is having two things, one is carry and the sum. So, each half adder is having carry and sum. So, this is the my last step, okay, where we can do the last step will be AND gate or OR gate. Further you cannot reduce it. So, this can be done individually. So, each blocks can be designed separately and then it can be combined together, so that we can have a 16-bit adder. So, this is called design hierarchy. So, like a system, if you are having a big system and if you want to assemble those system, then what kind of thing you can do? Suppose I have to design a I have to assemble the system, then you are purchasing RAM, you are purchasing motherboard, you are purchasing processor, and you are purchasing the power supplies. Okay, as so all this equipment you are combining within the cabinet. So, this kind of approach is called your design hierarchy. You are disassembling and you are assembling. This kind of approaches we have to adopt to simplify, to make it faster design approach. Clear? Thank you all.